All right, put your schedules away. Put your schedules away. And let's just chat because we didn't quite get done yesterday. So again, you don't need your computers actually open yet. I can't compete with the internet. Close your computer. And at this point, we're going to talk about vapor pressure for another maybe 2 minutes. We're going to do one more problem with vapor pressure, and then we're going to go on to colligative properties, like the rest of the colligative properties. All right. So what happens to this is just quick review. What happens to solubility of a gas when temperature is increased? Everybody? It decreases. Why? Relate temperature to what? What kind of energy? Kinetic energy. So I was just trying to get you to say kinetic energy, not just energy. So decreased solubility because increased kinetic energy, and those particles with the highest kinetic energy can do what? Overcome. I'm not going to just say surface tension, but what's holding the surface tension together? IMFs, and therefore, as they overcome IMFs, they then evaporate. So you've got to be able to put that into maybe a sentence versus just blabbing on for like a paragraph. Okay. All right. What is Raoult's law and what does it calculate? So me the back table. JT's yawning on me.
So it's like the relationship between pressure and concentration.
No, not gas. Somebody else at your table. You're doing Henry's law, yeah. Okay, first off, what does Raoult's law calculate? Back table. Vapor pressure, right? So vapor pressure, but of a what? Of a solution, which is different than the vapor pressure of pure solid. So now, how do we calculate the vapor pressure of a solution with a non-volatile solute? Mole fraction of the solvent, not the solute. So we care about the solvent because that is the actual thing doing the evaporation, not the solute because it's non-volatile. Times what? Vapor pressure of what? Pure solvent. And that's going to equal pressure of solution. Vapor pressure of solution. All right, so we're going to modify this a little bit when we talk about volatile solutes today. We were talking about non-volatile, which means that they don't re-evaporate to cause any pressure. In the end, like you should be able to give me a really quick snippet of what vapor or why vapor pressure is lowering. When you add a non-volatile solute, go ahead and talk to my groups first. Brief one sentence. All right, come back to me. 3, 2, 1. Jaden's table, pick up from there. Give me a quick explanation.
Whenever like the non-volatile solute reacts with something else, like in the solution, then it will like bring the vapor pressure down because that one will evaporate.
Okay, I'm not going to say react because react means like a true reaction. So what's another word we could say instead of react? Interact, or IMFs are at play, right? So the solute and the solvent have IMFs, and those IMFs are going to basically limit the kinetic energy of the solvent, which is going to limit the vaporization of that solvent. So basically things interact, they kind of pull each other down through attraction. And then definition of boiling is when what equals what? Vapor pressure is equal to, somebody just told me here. External pressure, the pressure of the atmosphere. I think that's probably more likely what you would say you're right. Okay, so we'll talk about vapor pressure lowering a little bit more. I'm going to go back to the slide we were at, so hold up. We were here. Yeah, we were here. And then I just wanted you to see like a picture to help you see the vapor pressure lowering. Before I talk, I think if you read those 2 paragraphs, it makes a whole lot of sense. It's a great explanation. You can see this. Sorry, I think this thing's goofy right now. Where my little extend button is. Alrighty. Alright, so essentially, why would there, like, according to this first paragraph, why would there be less solvent molecules on the surface? Why would there be less solvent molecules on the surface when you've made a solution? Okay, I'm going to say, I like the first part. So you have these little solute particles in here, right? And so the solute particles are starting to kind of distribute into an even fashion or diffuse. And with respect to that, there might be some at the surface, so then the percentage of solvent particles at the top is lower because you've got some that are displaced by solutes. And the solvents are moving down to begin to interact with during the solvation process with the solute, so therefore less of them are at the surface. And then you can see that the black ones are the ones that were replaced, so those are the solute particles. Therefore, fewer solvent particles able to go into vapor phase, lower vapor pressure. And that's all because of IMFs and interactions. Okay, so notice the change here. We're talking about what now? Two volatile substances together. The first scenario was like salt water, water and sodium chloride, something non-volatile like an ionic solute. Today, now we're just going to focus on two volatile solvents, or two volatile substances. They both can't really be called technically the solvent. But essentially what we're looking at is solvent, or compound A and compound B, where they're both able to vaporize. They both originally have their pure solvent vapor pressure, that's PA naught, and PB naught. When we multiply both of them by their own separate mole fractions, we get the new vapor pressure of A upon mixing and the new vapor pressure of B upon mixing. So what we assume is that we have A's vapor pressure and B's vapor pressure, and if we add them together, we just say, okay, A plus B gives me the total vapor pressure of this mixture. That is actually Raoult's law. This is the one we actually call Raoult's law, but everything's related that we've been talking about so far. So we're assuming that there's an ideal behavior that would give us this simple summation to give us the vapor pressure of the total solution. But remember, when we assume ideal behavior, when did we also do that? Ideal gas law. And I was like, psych, there's what? Say again? There's exceptions. There's no such thing as an ideal gas. There's such things as real gases. Remember, we had all those variations from expected behavior. So just like the ideal gas law, this is like the ideal solution law. We make this assumption to make our lives easier, but we have to accept defeat and say, okay, there must be some way where the vapor pressure or summation would not be exactly what we expect or exactly what we would anticipate. It might be a little lower, a little higher. What do you think would make the vapor pressure of two volatile solvents lower? Cassie? Perfect, stop there. Okay, if A and B interact with really strong IMFs, nobody's vaporizing, right? They're hanging out together. They're attracting. What would cause? Go ahead, make it crunchy. Okay. And then what would cause the total vapor pressure to be higher than maybe anticipated? What would make stuff just jump out of solution? Yeah. So weak IMFs, or even like so much that they repel each other, right? So that there's no attraction whatsoever. All right, so we're going to talk about that here in a second. Okay, so using this logic, you guys should be able to solve this question. I think I've typed this one. It's on your packet someplace. Copying your group says you need to, but you're going to be using two versions, like the first version and the second version of Raoult's law. Yeah, you can utilize the same unit that's provided. Check yourself when you get to the point where you're and let you process before you
Just like what was in the mold.
Alright, yes, ma'am. In terms of mass, usually if you're looking at the quantity, it's going to be based on a normalized unit, I guess. But
With this one, you only do the answer for the one with like weight salt to be greater mass.
I wouldn't necessarily ask for that because there's both of these are volatile, so they're both causing vapor pressure, so they're both considered important. So you wouldn't be asked for that unless it's a non-volatile solute. Okay. All right. So essentially, you just had two pieces of the puzzle, and you had to pull moles and moles for both. Get your mole fractions for both respective methanol and ethanol, multiply by their original pure solvent vapor pressures, noting that both of them have lower solution-based vapor pressures. Sum that up, and you get your new total solution vapor pressure. But what you can see here is original vapor pressure of methanol, original vapor pressure of ethanol. What should that sum? What should it sum to? Okay, so definitely over 100. But why are we here? Why are we about 70? Why is the vapor pressure lower for the solution? Because they can hydrogen bond. They're alcohols, right? So it's actually low. It's not only. I mean, this is pure and pure, assuming 100%, 100%. So these are relatively relatively high in their volatility. But when upon mixing, they're lower than maybe we anticipate. Not that you're able to anticipate 100% yet, but this is definitely lower, and we're going to say we're going to show the IMFs at play here, which is definitely hydrogen bonding. Yeah. I would give me an atmosphere is toward whatever unit's provided. I would use that unit. Don't waste your time converting unless it's asked of you. Okay. All right. So do I need to do this one? No, we're going to move on. Okay. This is on your paper. There's a graph on your paper provided to you, and this is just explaining how the graphs and the relationships between more or less vapor pressure upon summation occur. So, like I said, we do assume an ideality. We assume an ideal behavior. So we assume that upon mixing, the vapor pressure of the mixture is the sum of the vapor pressures of each substance. That's what we assume. We know that our assumptions are often just to leave us with easy math. That's just because we're still in intro chem. And then I'm going to let you see the positive and negative deviation explanations first, and then we'll look at the graphs for those. So feel free to write down the mixtures. You don't have to write down every word that's up to you. It might just make sense. So with the positive deviation, are we saying the vapor pressure is higher or lower than expected? Definitely higher, right? So the vapor pressure is higher. The only way that would happen is if basically there's some way the particles are almost more repulsive in solution than they were in their independent phases. So this is kind of what this first sentence is relaying. You don't have any IMFs between the particles A and particles B. Instead, they're more cohesive within themselves. So cohesive means sticks to yourself. And then as that is going to evaporate in its normal rate of evaporation, it's going to basically accumulate those vaporization pressures, make it summative, plus the fact that these don't like each other will almost make them evaporate faster. So negative deviation means vapor pressure is what? Lower than expected, and that's going to be because of the IMFs at play. And so if A and B like each other, they interact with strong IMFs, they're not going to evaporate at the rate that we anticipate. Therefore, the observed pressure or vapor pressure is lower than we expect. Good? So with those, we have graphs that are associated with them. We rarely see these graphs in the AP exam, but I want to leave you if you needed this help here. So what this graph is supposed to be kind of anticipating, you might even have a hard time seeing this, but this is mole fraction for A and B. A is increasing to the right and B is increasing to the left. And so essentially the vapor pressure of B and the vapor pressure of A sum to this right here, which is just PA plus PB equals P total. But as you can see, there's like a hump in both of these graphs. So they're saying that the vapor pressure of both of those are higher. Why would these vapor pressures of A and B be higher than anticipated? No interactions, right? And therefore we have another line we draw to indicate the positive deviation. And then that's A and B is greater than anticipated, or A plus B is greater than anticipated. And then these have kind of like a lower slope or a lower curve exponential. And as you sum those up, you get a lower vapor pressure. So those are the graphs that just sometimes relay the same information, but I think you guys are getting the point. Can I move on? Shake your heads or something. Okay. So I'm going to talk about colligative properties, and then we'll do our lab stuff. This is stuff we didn't quite get to yesterday. Okay, so two other colligative properties. We may not get to osmotic pressure today, but I can do that another day. So write down the two pieces up here, and then we're going to explain why this happens. And give me just a hand raise if you've calculated these in honors time. You like the delta T is equal to KIM. I was just seeing if others do it because it's kind of like the concepts are in our curriculum, but the calculations are more of an honors concept. So I was just seeing what everybody was. So boiling point's related to vapor pressure, right? What's the definition of boiling point again? Equal to vapor pressure. Okay. Definition of boiling again is when vapor pressure of the solution is equal to the atmospheric pressure. Now, we already know all about vapor pressure now. What are we doing to vapor pressure of a solution when we add a non-volatile solute? We are lowering the vapor pressure. We are lowering the vapor pressure because the solutes are mingling with solvents. Solvents are not evaporating at the rate they once were. So, why do you think that this is an elevation example and not a lowering example? Okay, so say that louder, because the vapor pressure of the solution equals the atmospheric pressure. At that point, that's when it boils, right? Okay. Energy. Beautiful. Okay, so essentially, if you lower the vapor pressure, you're then going to need more energy for vapor pressure to equal atmospheric pressure because the atmosphere is not changing. It's still the same pressure. And so upon you lowering that, you need to get the vapor pressure up to the point where it's equaling the atmospheric pressure, external pressure. And that's just going to require more energy. And if you happen to increase the energy and then it starts to boil, what have you done to the boiling point? If you increase the energy and now it's, let's say it's water, and normally it would boil 100, but I've adjusted and made the solution like salt water, and therefore I've lowered the vapor pressure and I've heated up more. And at that point, that higher temperatures at which it boils, I now have a new boiling point, and that boiling point is higher, right? Elevated. It's been elevated. So every single time we do boiling point, it's always boiling point elevation. And then separately, every time we talk about freezing point as a colligative property, it's freezing point depression. And so we'll get to that in a second. So what you need to know is that delta T is the actual elevation difference, the change in the temperature at which you're boiling. Kb is the Malal boiling point constant. Malal sounds like it's referring to molality, hence why we see the little m here. The m is referencing molality. Quick reminder, what's molality? Moles of solute over kilograms of solvent. Okay? And then lastly, we spoke yesterday of the I factor. Do you remember what that was called? Van 't Hoff factor. It's related to number of ions or particles that are forming. So a lot of times we call this delta T is equal to Kim. Delta T is equal to Kim because K is the Malal freezing point, or Malal boiling point constant. I is the Van 't Hoff factor, which is on the next slide, so hold up. And then molality is molality. So same equation is used for both boiling point changes and freezing point changes. It's just the only main difference is we're using a different constant. So delta T is the depression of the freezing point. So that delta T is just how much you're lowering. Kf, or KFP as sometimes it's written, is the, guess what that is? Malal freezing point constant. And again, molality is what little m is standing for. And then we also will include I. So the more particles you make, the more significant your changes are. So we have to include the I because covalent substances just don't affect boiling point and freezing point as much as ionic substances do. So to respectfully include the ionic substances and the particles they break into, we include I in this. And then maybe you can tell me, looking at the equation, delta T, K, and M, what should K's units be? If M is molality, it's a little m, and then T should be in what, likely? Celsius. If this is M, what's K? Don't break the M. Let's just keep it as M, as molality. See, so delta, or degrees Celsius over molality. Yes. So this right here is degrees C per molal. Okay, and those are constants I'll provide to you. Go ahead and write down two of them, though, because we'll use them quite frequently. The KB for water, this is a lowercase k, doesn't always look like it, but it's lowercase, 0.52 degrees C per molal, and this is for water. And then KF for water is 1.86 degrees C per molal. Those are the two most commonly used constants because a lot of times we deal with aqueous solutions. However, there's a table in your textbook. I also can always pull this back up for you if you have a non-aqueous solvent. Okay? All right, so read this because we talked about this yesterday. Write down what you need to. So what's nice is the I factor, the Van 't Hoff factor, is unitless, so it's not impacting our equation at all, really, outside of it being a multiplier. If you have a substance that doesn't ionize, what kind of substance would that likely be? Covalent. So if you have something like sugar, ethylene glycol, benzene, other stuff like that, you're going to have a I factor of 1 because it's staying as one particle overall, despite it being able to break apart from its other particles of its type. It still exists as one particle. Ionic substances like sodium chloride or magnesium chloride have an I factor of 2 or 3. Of course, these are predicted. We assume that 100% of those ions are breaking apart, but there is a phenomenon we see called ion pairing. And the ions can definitely they're ions, right? They're attracted to each other. So they can kind of come back together in solution. So maybe not 100% of sodium chloride will break apart to make 2 ions. There might be some that kind of stay together. Therefore, we actually can see some differences in what we predict and what we observe experimentally. So we expect I of 2, but we see an I of 1.8. So just note, we do a lot of prediction, but experimental data may show us otherwise. Okay? So far so good today, guys? Hopefully some a little bit of a teeny bit of review. All right, so we're going to do calculation. All right, I'm going to scooch forward. So freezing point, I want to know the freezing point, meaning like the new freezing point and the new boiling point of a solution prepared by dissolving 651 grams of ethylene glycol in 2,505 grams of water. So before we move from here, this is our solvent, right? Pure solvent, what is the boiling point? What's the freezing point? Okay, so 100 degrees Celsius is the normal boiling point with no additives, meaning pure solvent. And then what? 0 degrees Celsius. So we have to do a comparison to the normal in order to get the new. Okay, so with this, let's just do one at a time. Let's do boiling point. What is the equation to find the delta T, the change in elevation of the boiling point? Delta T is equal to, I heard Kim, right? So, and this is just K is what? KF or KB? KB. KB. Okay, and then KB for water is what? 0.52 degrees C per mole, your units. I, for this particular species that's being added to water is what? Why 1? It's, come on guys, what is this? Covalent. It's covalent, 100%, not going to break into many parts. So I is 1 because it's, remember, ethylene glycol is a, what's antifreeze? You put it in your car, radiator, basketball goal bases, stuff like that. You know what I'm talking about, basketball goal base. You don't want it to freeze. Like a movable basketball goal. Alright, so sometimes you guys look like me, I got 2 heads. Okay. Alright, then molality. What's the molality going to be referring to? Moles of ethylene glycol over kilograms of water. Take a hot second, get your molar mass. I can tell you as soon as I find my paper. Yes, okay. And you know, like, I could easily do this in the calculator, but I'm showing you the work because I expect that you're showing me the work. And on the AP exam, you should always indicate, even if it's a simple conversion like this, always indicate your work as support. Because you really don't know when you get points for work. What did you guys get for your delta T? 2.118. I'm just choosing a number for us to move on, but it depends on how many sig figs you included throughout, of course. There should be not too much of a discrepancy though. So, regardless, this is our boiling point what? Elevation. So normally the boiling point of water is 100. What is it now upon addition of ethylene glycol? So we're doing the normal plus, so elevated plus 2.16. So we get the new boiling point to be 102.16. Yay! Okay, so normally North Carolina doesn't really get that hot, so your ethylene glycol, which is put in your radiator or basketball goals, will not boil, which is really good for your radiator. All right, you guys do freezing point. Very, very simple process. No, but you're thinking acid and base. KF. I know, when I was looking at this last night, I was like, oh, we just did equilibrium, and everyone's going to think of K as the equilibrium constants, but they're not. What's your freezing point change? 7.796, so 7.8, let's go with that. But we had 368, so 80. Okay, so this is your delta T for freezing point. What is your new freezing point? Right, so you're doing 0 minus the delta T, so minus 7.80, and that's negative 7.80. And that is our new freezing point, and it likely is not going to get like here anyway, close to negative 8 degrees Celsius. So our radiators are just safe as can be. They're not going to freeze, and your poor basketball goal space will be fine. Okay, so those are 2 examples. Are we okay with those? Those are just calculating delta T. So occasionally you'll also have to calculate molar mass of the given solute. So backtrack here for me. If I want to find molar mass of the solute, what 2 pieces do I need? Maybe not molality yet, because we're going to back up there. So what are the units of molar mass? Grams per mole. So we need grams and moles, right? So if you look at this question, you already provided what? Grams. So we must find what? Moles. And then using this whole equation, where is moles going to appear? Molality. So that's my tip for you. Go ahead and try to report. For benzene, 5.1. Hold on. Benzene is KF 5.12. I'll write that up here. So I will make a note. He asked me for the benzene one because we have to have the KF for the solvent. In this question, the organic compound is a solute. Who's the solvent? Benzene, right? Not water. So that's why you need a different K value, because it's regarding a new solvent. Yeah. Does that matter? Hold on. Well, it does. Dang it. Hold on, guys. I don't remember that one off the top of my head, so it is 5.50. 5.50. So the normal freezing point of benzene, 5.50. Sorry, I was thinking you just need a delta, but you need the whole thing. You need to get the delta, so you need the whole thing. All right, I think I've provided you all the necessary info. Dang, why does it say 0.9? All right, everybody help me out here. What's your delta T for this question? Say again, delta T. Okay, so you're taking the original 5.5, you're comparing it to the new, what was the T? 0.38? 4, sorry, degrees C. The K value was 5.12 degrees C per molal. In different textbooks or like online, sometimes they publish these a little differently. So if your answer like on a problem set or something's a hair different than mine, it's just because of likely constant being slightly altered. I factor for organic substances would be what? 1, and then we're just looking for molality. When you solve for molality, what do you get? 0.0664. Okay, and then this is M, which is equal to whatever what? Okay, moles of solute. I was going to put it down, but don't know it. Over what? So we have the kilograms, or we have the grams here, so what's the kilograms? 0.1 kilograms of benzene. So multiply by 0.1, and you get moles to be what? 0.0664 moles. And then getting down to molar mass, you do what over what? 0.85 grams over 0.00664 moles, and you guys get what? 128 grams per mole. Woo! All right, so that would be an example of, like, you know, we're organic species, right? We have organic everything, so every life form on the planet. But you guys know those frogs that they freeze, but then they hibernate, but they freeze, and in hibernation they come back. They actually can figure out what's in the cells of those frogs in some way or form with things like this. Okay, so like they can lower their freezing point to a certain point, so we can get the delta T, and there's substances, there's organic solutes in their bodies that can do this, and they can figure out what the substances are and use them for other things based on like molar masses and amongst like a million other tests, but this is a cool example. I thought that was cool. Okay, let me make sure I'm good. Oh, this is the last thing I'll do for today, and then we'll go into our lab. So recognize this as what? What's this thing called? Phase diagram, right? Solid, liquid, gas. And then each of those lines represent what? So all of these lines here represent freezing point or boiling point, right? Because it's the difference between the solid and liquid phase, so it depends on which way you're going, but it's the physical equilibrium between the solid and the liquid. And all the points here represent the physical equilibrium between the liquid and gas, also known as boiling points or condensation points, right? So essentially what we're doing is we're modifying this graph. This might be the pure solvent, and it's got 1 point of boiling point or freezing point and boiling point at a particular pressure. So what are we doing when we make it a solution? What are we doing with this line from A to B? Moving it left or right? So this is freezing point. All points here are representing freezing point. We're moving it left, and it's just going to be by a delta T. Like whatever remember this attempt down here. Whatever the delta T is, it's going to be across the board. So all of this line is just going to move to the right by the same amount. And then when we do boiling point, what are we going to do? It's going to move to the right because all these points here are representing boiling point. So we make this a solution. We'll change the properties by a certain delta T, and so the delta T will move up. So we basically can do our graph in such a way to indicate the new points that matter for a solution version of the solvent. So you could easily get delta T's from a graph standpoint as well. So that's what like this is supposed to be indicating, and these two. Okay. So I just want to show you another example of where you could pull data from it if needed. And we're going to wait on osmotic pressure. Okay. Open up your laptops. I have something in class I'll do first 10 minutes. That means so we're basically going back to the doc that we started on yesterday. So open up your Google Docs as well as under homework. Well, you guys have it copied on your Google Doc most likely, unless you just started on a clean slate. Where it says Tuesday, pre-lab for sticky molecules, student doc. So give me a thumbs up if you made it through both videos yesterday and you took down like 5 to 10 bullet points of just some information. I think that's really valuable to have done because that gives you the premise of how to do your procedure. Like you almost have the basis of your procedure thought out at least. And then down at the little simulator, it's a quick simulation. You just change 2 variables, absorption and rate of evaporation or whatever, and you're going to answer those questions. Who's maybe partially through this? Okay, a couple of us. All right, so finish that up for now, and then if you are ready, you're going to go to concord.org. It's called Concord Consortium Molecular Model or something like that. But it definitely requires Java. So I need to make sure that you can click yes, like allow now or run now when you get to that piece. Because essentially, when you go here, I'll kind of show you how to get there. So it tells you, hold on, it tells you to click more. I have put this someplace here. Intermolecular force of attraction, and we're going to hit more. So this is kind of what it looks like, but if you watch me, I can kind of show you this. This is your kind of landing page, and as you go down, you see all these just great simulations. None of these are what we want. None of those. We're going to hit more modules right here. So when you hit more, they're going to ask you to download something. It's going to launch a piece of software, and that's going to come down here. Yes, it's safe. So hit keep. Maybe. You might actually have to click it again. Once you hit keep, hit it again so it'll actually launch. So I'm gonna see if we can all get there. Hit later. If Java's trying to update, hit later. Do not do the recommended option. Hit later. And then you can hit run.
Which one do you click on?
You hit more modules right here, and then it'll download Java, and then this will come up. I can do this again, but I'm just trying to give everybody a heads up on what's happening here. And then you're able to look for the IMF's one, which is going to be intermolecular force of attraction right here in the middle. It's going to hover. So basically, catch up on piece wherever you are, and then we'll talk. I'm just going to Yeah, my goal is to allow you to do the Concord Consortium thing in class, because one, it's a Java-based software, and I'm not sure that's always accessible at home. And two, I just want to see how far you get, and then I'll decide whenever you're good to go. So there are a couple of interactive pieces that you'll want to see the particulate diagrams for, because you are required to draw some particulate diagrams, and I think we definitely want some of these on that. If anybody needs help getting to this, just let me know. You will have to hit create a report as it indicates in the instructions on your Google Doc. So that report helps me see how far you got. That's why I kind of want you to jump on that today in class, like now, so you can get pieces of it done. You're not doing it on your own. Because the other part, really, that's easy enough for you to do on your own if you need to. All right, eyes up here, and 3, 2, 1. Eyes real fast. Okay, so the next piece for about 10 minutes, I'm going to have you go ahead and approach is 1, look at the purpose of this lab, which is in your reading, not on the Google Doc, because I only put so much on here. So the lab I gave you yesterday, pull it out for me. And I'll give you the quick premise, and that I spoke of this yesterday, but you maybe forgot. You were getting a mixture, and your job is to separate the mixture. That's it. Just try to separate the mixture. But you must do it using chromatography. And chromatography is the process that you learned about in the second part of the pre-lab. So knowing the process is one thing, but choosing the materials and why you're choosing said materials and what results, like what does a positive result look like, what does a negative result, based on the material that provided you, or you provide yourself based on the materials that are offered. That's up to you, okay? So I need to see in a Google Doc materials that you need, which are on the hard copy of the lab, so select from there. The procedure, as detailed as you can make it so I know how much you're using. What were the 2 limitations I provided you? 20 milliliters of a solvent, and you must choose choose 2 solvents to utilize for your separation technique. That means 2 different trials, right? And then you can you're only allowed 20 milliliters of each solid. And then from there, make sure you also list any safety and disposal information, okay? So I'm gonna let you guys choose groups. You have a minute. Get together. It'll be about 4 people per group. If I need 3, that's totally fine. Maybe sit with each other. Go. You know, let's mix up a little bit. Try to get at least one new person in your group than normal. I know you're normals. So try to get one new person.
That means we have to exclude.
Oh no. They won't. Okay, I can select groups for you. Okay, get in groups. You have a minute. Like, move your body. Don't be children. You can do it. Marcus, talk to these ladies. All right, you have like 5 minutes to share Google Docs, and then you sign what needs to be done. Are you 4? Marcus is 4. Yeah. Alright, these are your groups. Make a shared Google Doc and then decide what you need to do from there. You probably want to look at your hard copy for a lot of this.
Wait, I have a question.